So let's continue on. Going on here, it says determine the limit of each function shown in figure 2.40 as x approaches 1 from the left and from the right. So here's the graph of f of x equals 1 over x minus 1 squared. Again, we could get this using Desmos, but it is provided for us, which is nice. The first question would be, what happens as x approaches 1 from the left? Remember that negative sign means from the left. So I'm going to come in here from the left. Let's see what happens. Notice what's happening to my y value. Well, it looks like my y value is going up and up and up, meaning that it's increasing without bound. We would say infinity. Okay. Likewise, let's look at the next one. Again, it's a plus sign there, so it means the limit as x approaches 1 from the right of 1 over the quantity x minus 1 squared. And if I come in from the right, as I approach x equals 1, I'm going up, up, up. So again, this would be infinity. So if someone said what's happening at that point, you could say, because the left and right agree, you could say the limit as x approaches 1 of 1 over x minus 1 quantity squared. Because they approach the same direction, you could say the limit, it's not that it exists at the point, it doesn't exist, but you could say the behavior approaches infinity. So we would say equals infinity. Versus, let's look at the next one right here. This is f of x equals negative 1 over x minus 1. Let's come in from the left on this one, just like we did on the previous one. So here's x equals 1. As I approach that value from the left, my y value gets bigger, bigger, and bigger. So this would approach infinity. As I come from the right, I'm coming from the right of 1. I put my finger on the graph. I trace it. Notice my y value goes down, down, down. So it decreases without bound, approaching negative infinity. Notice from the left and from the right, we don't agree on this one. We have infinity and negative infinity. So if they said, what's the limit as x approaches 1 of this at the point, not just from the left or from the right, we would have to say does not exist because the two sides don't agree. Okay. So what is formally then a vertical asymptote? It says if it were possible to extend the graphs in figure 2.40 towards the positive and negative infinity, you would see that the graph becomes arbitrarily close to the vertical line x equals 1. So it approaches, gets closer and closer to x equals 1, but it doesn't actually get there. Okay, and it says this line is a vertical asymptote of the graph. I want you to be very careful in the definition here. It says if f of x approaches infinity or negative infinity, as x approaches c from the right or left, then x equals c is a vertical asymptote. And what do I want to emphasize? Here's what I want to emphasize. It is x equals c. It's not something like, if I say what are the vertical asymptotes, it's not like x equals 2 comma negative 2. Those are numbers, and we're not talking about a number for x. We're actually talking about the equation of a vertical line here. So it has to be, if you had two vertical asymptotes, let's say at negative 2 and 2, you would have to write x equals negative 2, comma, x equals 2. So you do need x equals for each individual value here. It is a vertical line that we're talking about. Okay? So another thing here is if it is a vertical asymptote, just to let you know, then it cannot be continuous because it is not defined at that point. Even if it was defined at that point, the limit does not exist. So it says in example 1, note that each of the functions is the quotient and that the vertical asymptote occurs at the number in which the denominator is equal to 0. The next theorem generalizes this observation. Okay, so what are they saying? To find vertical asymptotes, it's where the denominator of a rational function equals 0. But that's not quite right, so let's go to the next page to discuss that theorem.